Here's the last multiple choice question from the Calc BC Bluebook test preview, and it says a function has derivatives of all orders for all real numbers. We know that the fourth derivative, the absolute value of the fourth derivative of x, is always going to remain less than 12/5, and the absolute value of the fifth derivative of x is always going to remain less than 3/2 as long as we remain on the interval 0 to 2. It says p sub 4 of x is going to be the fourth degree Taylor polynomial for the function based at 0. The Taylor series for f based at 0 converges at 2. Of the following, which is the smallest value of k for which the Lagrange error bound guarantees that the exact error between the actual value of f of 2 and the fourth degree polynomial's value evaluated at 2, the magnitude of that remains less than or equal to k. Now, what threw me initially when I was looking at this question is the fact that they used k here. I'm used to using k as the index of a series, right? K or n would probably be the two things that you use most frequently to represent the index of a series, and that is definitely not how it's used here. What's specified over here is the exact error between the actual function value and the fourth degree polynomial's value at 2. So we want to establish the Lagrange error bound. We're not identifying a value of the index, even though they're using a variable that we typically would use to represent an index. So we need to establish the Lagrange error bound for this fourth degree polynomial approximation based at 2. So I'm going to first start by finding the fourth degree remainder based at 2. So I would go to the next derivative evaluated at z. Z is somewhere on the interval where the series is based, which in our case is 0, to the spot where we're making our estimate, which is 2 in our case. I'm going to divide by the next factorial, and then I'm going to multiply that by x minus c, 2 minus 0, where we're making the estimate, minus where the series is based, raised to the next power. So Taylor's theorem says that there is some value z that when plugged into this expression here makes up this exact error perfectly. The Lagrange error bound is the maximum value of Taylor's remainder based on where z has to fall. Well, since z has to fall in the interval 0 to 2, and the fifth derivative on the interval 0 to 2 always has a magnitude that's smaller than 3/2, I can put 3/2 in place of this numerator. Kind of adjusted some things just based on how the answer options are presented. I bumped the 2 to the 5th into the numerator of the fraction, left the 5 factorial in the denominator, and just put the maximum value of the fifth derivative evaluated at z right beside that initial fraction. And if you're looking at these answer options, we have built the Lagrange error bound represented by option A.